In this video, we'll cover section 2.9 on applied optimization. The objectives of this video will be to cover word problem solving techniques and look at applications in the realm of business. When attempting max and min story problem techniques, we'll start by translating the English statement of the problem line by line into a picture if it applies, and then into math. This is often the hardest step. We'll identify the objective function, look for words indicating a largest or smallest value. Oftentimes you'll be asked to minimize or maximize something. If you seem to have two or more variables, find the constraint equation. Think about the English meaning of the word constraint and remember that the constraint equation will have an equal sign. Then we'll solve the constraint equation for one variable and substitute it into the objective function. Now you have an equation of one variable. Use calculus to find the optimum values, that is, to take a derivative, find the critical points, and test. Don't forget to check the endpoints. Look back at the question to make sure you answered what was asked, and then translate your answer back into English. Some key ideas to remember for business applications. Profit has critical points when the marginal revenue and marginal cost are equal. Average cost has critical points when average cost and marginal cost are equal. The total cost in dollars for Alicia to make Q oven mitts is given by C of Q, which is 64 plus 1.5 Q plus 0.1 Q squared. Please note that I had to add in the 0.5. We'll start by identifying what the fixed cost is. Fixed cost is when no units are produced, and so we'll want to evaluate our cost function, our total cost function, at 0 mitts produced. We end up with a fixed cost of $64 when no mitts are produced. This is the bare minimum cost of running the business. That might be keeping the lights on, paying any salaries, and it might be that the 64 is in terms of thousands as well. So we would need more information to see the realistic part of this. In part B, we'll want to find a function that gives marginal cost. Remember that marginal cost is the derivative of the cost function, and so we'll take the derivative of C of Q. The derivative of the total cost function is 1.5 plus 0.2Q. In part C, we'll want to find a function that gives the average cost. Average cost is taking the cost function and dividing by the number of units, so it's cost per unit. Our average cost function is then 64 over Q plus 1.5 plus 0.1 Q. It may be helpful to write this as 64 times Q to the negative 1, which will make taking a derivative easier if necessary, which it will be in the next part. Part D says to find the quantity that minimizes the average cost. So here's our objective. It's to minimize our average cost. That tells us that we'll want to take the derivative of the average cost function. The derivative of the average cost function will be negative 64 Q to the negative 2 plus 0.1. And we'll write this back into negative 64 over Q squared plus 0.1. Because we want to find the quantity that minimizes the average cost, we need to first find the critical number of the derivative of the average cost, and then we will set the average cost equal to 0 and solve. When we take the square root of 640 to isolate Q, we see that the approximate critical number is 25.3. We need to make sure that this is in fact a minimum, and we'll do the second derivatives test to verify. So I'll take the second derivative of my average cost function. So the second derivative is 128Q times negative 3, or 128 over Q cubed, which we'll use to evaluate our critical number. Since the output is positive, the average cost function is concave up around the critical number, implying that it has a local minimum. And so we would have that 225.3 units will minimize the average cost. Part D asks to confirm that the average cost and marginal cost are equal at your answer. So we'll plug in 25.3 into our marginal cost function and compare it to the average cost also evaluated at the same value. The marginal cost evaluated at 25.3 yields 6.56. That would be dollars per unit because marginal cost is a rate of change. We'll compare this to the average cost also evaluated at 25.3. The output is also 6.56 units dollar per units, and so we have verified that they are in fact the same at the unit that minimizes average cost. The next video will review other applications of optimization.